Hello and welcome to Section 5, Features. So we now finished talking about what a predictor is and how one evaluates predictors. And we can start to move on by talking about how to construct predictors. And the first step in the process is taking the data in its raw form and embedding it into vectors. And I want to establish with a little bit more formality right now exactly how we do that, and talk about a variety of different ways in which we embed data in vector space so that we can use mathematical techniques to construct predictors. We have raw data pairs, which we will denote by U and V, where U is in some script U, which is the set of possible U's, and V is in some script V, the set of possible V's. And here, script U is the set of all possible input values, and script V is the set of all possible output values. And ideally, our predictor is going to take an element of script U and return for us an element of script V. The elements of U are called records, and typically they're a list of attributes of the data. These attributes, which will index the UIs, are called fields or components of the data. And notice here the I here is a subscript on U. When we use a superscript, that means the ith record. When we use a subscript, that means the ith field of a record. And each of these fields has a type. It might be a real number, it might be a Boolean. It could be one of several different types. It could be a piece of text, it could be audio, it could be an image, it could be a parse tree, an output of a compiler. There are also certain generic types that we talk about, categorical and ordinal types, and I will tell you what those are shortly. For example, you might have the set U be a set of houses, and then a record would record the properties of a house. So it might give us its address, a photo of the house, perhaps some photos of inside the house, a description, which is a piece of text, a categorization of it as either a house or an apartment, the size of the lot, the number of bedrooms, and so on. The list goes on. And our goal with all of these things is that we're given all of this data and we're trying to predict, say, the price. How much did the house sell for, or should the house sell for? And notice that each of these fields of the description of a house has a type. So address, well, that might be text, or we might be a little bit more precise about what an address is. It might be have a street number and a street name and a city and a county. We might have GPS coordinates for the location of the house. The description is text, but even there we might be able to be a little bit more refined about that. We might have description of various parts of the house. We might have standard forms for the description of the house. And so how we take this data and embed it in vector space is going to affect a lot our ability to make useful predictions using it. So abstractly, the functions that we use to do this embedding are called the feature maps, and we have two of them. One of them takes U and embeds it in d-dimensional vector space and gives us X. The other one takes V and embeds that in m-dimensional vector space and gives us y. And learning algorithms are applied to xy pairs, which are just vectors. And the functions are called phi and psi. So phi takes a u and gives us an x, and psi takes a v and gives us a y. And these are the feature maps. They transform data records into vectors. Usually feature maps work on the separate fields. So we'll have a feature map that maps the photograph into a vector space. We'll have a feature map that maps the address into a vector space. And so we've really got a different feature map for each of the different fields of a particular record. And then we'll construct one feature map which takes the entire record and maps that into a vector space. And the way it does it is by mapping each of the fields of the record into each of their component vector spaces and then joining up all the vectors into one long vector. So phi subscript I is an embedding. It's a map which takes field I into a vector. And the overall function phi is the feature map that combines all these embeddings and takes a record into a vector. The reason we do this is so that we can put all the different field types on an equal footing. They're all vectors. And some of these embeddings are very, very simple. So if the raw data is actually just a real number, such as the lot size of the house, then we might just embed it by using the identity map. We'll just embed it according to x is equal to u. Sometimes a field may be Boolean, and so for example it might be for a house it might be has a pool, and the answer could be yes or no, and in which case we would map that to a real number in a vector space by saying 1 if the answer is yes and -1 if the answer is no. Or we might map it according to 1 if yes and 0 if no. Color, we might map to 3 numbers. The amount of red, the amount of green, the amount of blue. And that's a very typical encoding for color, which we use a lot for images, but it's by no means the only one. And there are quite a few different standard color encodings. There are also much more sophisticated encodings, which we will have a chance to talk about later. So one is if one has a text document and one wants to embed that as a vector, then there's a map called the TF-IDF map. That stands for Term Frequency Inverse Document Frequency. And we'll see exactly what that is and why it's useful for learning properties of text, building predictors for text. Another one for text is called Word2Vec. We'll see that in just a second. That maps individual words into vectors rather than mapping whole documents into vectors. Another one is that instead of thinking about an image as a collection of pixels, we use a particular feature map to map the image into vectors. And these are pre-trained neural networks. We will see an example of this very shortly. One of the things we want out of an embedding is that it should be faithful. And what that means is that it should somehow preserve similarity. So if u and u tilde are 2 different records, but somehow they're similar, they correspond to 2 similar houses, then when we embed them, we get a phi of u and we get a phi of u tilde, and those 2 vectors should be close to each other in the vector space. And conversely, if phi of u is not near phi of u tilde, well then u and u tilde should be dissimilar houses. And so the geometry and the distances within our vector space should somehow correspond to our intuitive notions of similarity for our underlying raw data. And this particular notion of similarity, well, it depends on the application that we have in mind. It depends on the field type that we're looking at. For houses, we have some idea of what that means. They should be similar size, they should be similar quality of construction, they should be similar types of houses, similar numbers of bedrooms. We have some idea of what that means. And for many other things, it won't be so obvious as to what it means in any numerical sense, but it might be obvious in an intuitive sense. We know that, for example, two images that are both images of cats are similar to each other, but they're distinct from an image of a dog. And that's something that we're going to have trouble quantifying. We'll see there are ways of embedding in such a way as to have a faithful representation of such things, and we will get to those. So there are lots of interesting examples one might think about where it's not so obvious how to construct a faithful embedding. We can think about names of people, professions, companies, countries, languages, zip codes, cities, songs, movies. And we're going to see several of these in examples, and we'll also see some general techniques for constructing embeddings. Here's one. Suppose you have location data. You have the position of something on the world. So you might describe that by two numbers, the latitude and longitude. That would give us a two-dimensional vector in R2. Or you might say, really, this should be embedded in R3. We think about the world as a globe, and the globe has a natural embedding in three-dimensional space, and so we can embed our position in on the surface of the globe as a position on the sphere in R3. Maybe that makes more sense if your data points are spread over the planet. Here's another example, the day of the week. So we have Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. We could just label them 1 through 7, and that would be an embedding. We should embed the day of the week into a one-dimensional vector space. Also on this slide we see a two-dimensional vector space. This is interesting. This is useful because for many types of data, the similarity between days is that a day is similar to the day before and a day after. And if we were to embed Monday as 1, and Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday as 7, then 1 and 7 would be quite far apart, and so Monday and Sunday would be quite far apart. If we embed them like this, so here we've embedded them as 7 points in R2, well then we can see that the distance between Monday and Tuesday and the distance between Monday and Sunday, those two distances are the same, and indeed the distance between any two consecutive days is the same. And so this is an embedding that more faithfully captures that idea. And we can do that for lots of different notions of time. We can do that for months of the year, which we might embed as 12 points. We can do that for hours of the day, which we might embed around the circle as 12 points around the circle. Here's a more sophisticated example. This is word to vec. And that's a mapping on words. So you give here the field type is a word in the English language, and word2vec, for each word in the English language, it will map it to a vector, and that vector is a 300-dimensional vector. And so word2vec actually will work on words and short phrases. It doesn't just include dictionary words, but it also includes names of people and names of places and many other things. And it's developed from a data set which comes from Google News, which contains 100 billion words. And so this is not a hand-constructed embedding or hand-constructed feature map. This is an automatically constructed embedding. And we will say more about how that is done later in the class. The principal idea here is that words that frequently appear near each other should get nearby vectors. And so we might look at that. Now, of course, it's hard to look at the specific vectors that correspond to word2vec because they're 300-dimensional, and so we can't plot them. But of course, we can use them for all sorts of predictor construction. However, here we can just plot some of their components. So here are two of their components, x1 and x2, of a bunch of different words. Let's zoom in a bit here. And so you can see, even when you look at a two-dimensional projection of this 300-dimensional vector space, you can see that words that sort of mean similar things are kind of close together. Let's look here. We've got optimistic. Let's see if I can make that a bit smaller. We've got optimistic, proud, enthusiastic, happy, satisfied, eager, interested, amazed. These are all kind of next to each other down here. We've also got melancholy, sorrow, hostile, bitter, awkward, guilty, anguished, hopeless, vengeful, lonely. All kind of negative words sitting at the top there. We've got some others. We've got some irritated, exasperated, angry, embarrassed, frustrated, scared. All of these kind of similar words over there. And so these are just a selection of words. There are emotion words, of course. There are 3 million words in the database. And this is just a two-dimensional projection. But nonetheless, one can see what it does in terms of grouping. There are also some interesting properties of word2vec, some nice other types of faithfulness of the data that comes out. For example, if I take the vector for king and subtract the vector for man, and then I add the vector for woman, then the closest vector that I get to the result is the vector for queen. Similarly, if I take Rome and subtract Italy and add France, then the closest vector I get is Paris. And so these kinds of things are somewhat surprising properties of the embedding that are quite magical, but illustrate the point that somehow the embedding is capturing the structure of the relationship between words, which is what's going to enable it to be useful when we actually use it for learning. Let's turn now to a sophisticated method of embedding image data. And this is called VGG16. So ImageNet is an open database of images. It contains about 14 million labeled images in about 1,000 different classes. And they range over all sorts of different things. They include many images of animals, of vehicles, of everyday objects, shoes. It's a very broad collection of images, but they've all been labeled, and so we know exactly what is in each of those images. So VGG16 is an embedding which maps images to a vector in RD, and here D is 4096, so we get a 4096 long vector. And the images that we start with are all cropped down to 224 by 224 pixels. They're color, so they have RGB components, and that is some 150, 160 odd thousand components, 160 odd components of each image. And we have 3 numbers per pixel. And so we're going from what we might think of as a vector in 160,000 dimensions, and we're mapping it down to a vector in 4096 dimensions. And VGG16, it's a neural network, and it was originally developed to classify the images, and so it learned from the ImageNet database a way of mapping images to labels. But it's also been repurposed as a general method of constructing a feature map. It's a general method of embedding images in vector space. This particular neural network has 16 layers, and its input is an image, and its output is the vector in R4096. Let's look at what it looks like. So here are 6 different images. They're each 224 by 224. Image 1 is simply the Ubuntu mug. 2 and 3 are some guy. Image 4 is Professor Stephen Boyd. Image 5 is a car. It happens to be a mini traveler edition from the 1960s. And image 6 is a London bus. For those of you who haven't yet figured out from my accent, I am English. And this particular car is actually exactly the same type of car my family drove about in when I was 10 years old. And this is exactly the kind of London bus that I would have ridden on back in those days, although the car that we had was blue, not green. So let's take these images and embed them under the VGG16 map, and for each one of them we're going to get a 4096 long vector. And what we've done here is looked at those images in pairs, and for each pair of images computed the distance in terms of the Euclidean norm between the 2 corresponding embedded vectors. So let's look at this embedding. The matrix here is a matrix of the pairwise distances between the embedded vectors of each of the images. So, for example, this number right here is the 2, 3 entry of the matrix, and so that's the distance between image 2 and image 3, both of which are images of me, and so we expect them to be close if this is a faithful embedding. If we compare that distance between with the distance between image 2 and image 5, well, then suddenly we're looking at a number of 109 compared to 63, which is substantially different. And we can see that the 2 images of me are rather close to each other, whereas image 2 is quite far from an image of a mini. And same for the distance between an image of me and the image of the bus. Those are also quite far apart. And the same is true for the other images of me. Image 3 to image 5 and image 3 to image 6 are also quite far apart. And if we compare Stephen to the bus and the car, he's also quite distinct from a bus and a car. However, the distance between image 2 and image 4, we're both people, those are both headshots. We can see that those numbers are quite a lot smaller than the corresponding distances between humans and people. If we compare image 3 and 4, that's the other image of me and Stephen, they're also quite close. There's one more interesting pair, that's comparing the vehicles. So that's this number right here. That's the distance between image 5 and image 6. So that's this distance right there. And we can see that the two vehicles are considered much closer at 86 than a vehicle and any person, which are all about 100. So this embedding is faithful. We can also look at the images of the mug. You can see that the images of the mug are all quite far from all of the other images in terms of Euclidean norm distance. And so we can say, well, this is a reasonably faithful embedding. It's surprisingly effective at figuring out that three faces are kind of similar to each other, two vehicles are kind of similar to each other, but faces are really different from vehicles, and mugs are different from faces, and mugs are different from vehicles. Notice here that we didn't give it data that it had been developed for. I picked these images from some other source. None of these images are, as far as I know, on ImageNet. And so here we're repurposing a trained set of features, and we're using it for completely different images. And that sort of idea where one takes a model that has been developed using a particular data set and then uses it for a different learning task is called transfer learning. Now, we usually assume that an embedding is standardized. That's not always the case, but it is very often the case. And certainly when we construct embeddings by hand, we go out of our way to make sure they're standardized. And what that means is that they're centered around 0 and they have an RMS value around 1. And of course that means for a particular data set. We take all of the records U in a data set and we take each of them and embed them under phi, so we get a whole bunch of phi u's, which is a bunch of vectors, and that set of vectors should be centered around 0, and that set of vectors should have an RMS value around 1. And so that means that roughly the entries of phi of u range between plus and minus 1, very roughly. And with standard embeddings, that means that if I've embedded each of these features, phi 1 up to phi r here, into to have this property that they're all centered around 0 and have RMS value around 1, that means they're all comparable. A large value of x1, which is phi 1 of u1, and a large value of x2, phi 2 of u2, will both be around 1 or 2, and a small value will both be around minus 1 or minus 2. And it means that we can compare them. We don't need to worry about what units the original data u1 and u2 was in, or what magnitude they naturally have. We've normalized. And we might measure the distance between two embedded vectors using the RMS. And so we take the RMS of the vector phi of u minus phi of u tilde. That's a reasonable measure of how close records u and u tilde are. That's, again, a consequence of the faithfulness of the embedding. And so the way we ensure that all of our data has this property that it's centered at 0 and has values that range between plus and minus 1 is we do what's called standardization. It's also called z-scoring. So suppose we've got real numbers in the field type, and then we've got u1 through un, which are real numbers. Then what we might do is we might define u bar to be the average of the ui's, and stud u to be the standard deviation of the u's. And then in order to construct a vector, or in this case a scalar, x, which is an embedding of u which is normalized, we do what's called a z-score transformation, where we take u, subtract from it u bar, and then divide by the standard deviation. And that ensures that, first of all, that the average of the x's is 0, and the standard deviation of the x's is 1. So these are very easy to interpret all of a sudden. If I've got z-scored features and I look at x and I see an x which is 1.3, well, that means that the corresponding u is 1.3 standard deviations above the mean. Now, another transformation we might do before z-scoring is taking the log. Now, this is a very standard rule of thumb. If you've got a field u, which is a positive number, but it ranges over a very wide scale, then you embed it as phi of u is equal to log of u. Sometimes you'll use log of 1 plus u if u is allowed to be 0, and then you'll standardize. So, for example, if u is the amount of traffic that a particular website receives, well, then you've got a bunch of different websites, and each one has a different amount of traffic, and there is a huge difference between the amount of traffic that the big websites like Amazon and Google receive and the rather smaller websites such as my own website receives. And these are many, many orders of magnitude different. And so with this kind of thing, it's much better to, instead of trying to look at numbers over such a wide range of scales, to take the logs, and then we might conclude that, well, 1,000 and 1,100 are very similar. 20 and 22 are also very similar. But 20 and 120 are not similar. If we were to measure those in absolute terms, we might say, well, 20 and 120 are 100 apart, and 1,000 and 1,100 are 100 apart. And so we should consider them both equally similar. And 20 and 22 are only 2 apart, so they're very similar. But actually, if we look at it in the log scale, we'll find that 20 and 22 and 1,000 and 1,100 are both equally different or equally similar, and 20 and 120 are much further apart. And because we're taking logs, what we end up measuring is the relative difference between the values rather than the absolute difference between the values. Another way to say it is that 22 is only 10% more than 20. 1,100 is only 10% more than 1,000. And here's an example for house price prediction. We want to predict the house selling price, V, and we've got a record, which in this case just has 2 fields, U1 and U2, U1 is the area in square feet. U2 is the number of bedrooms. We care about relative errors in price. So we're much more, we can say if two house prices differ by 10%, we will consider them as similar. And that allows us to consider $1 million and $1.1 million as just as similar as $100,000 and $110,000. And so we'll embed the price V as using psi of V as log V. And then we'll standardize. We also standardize the records U. In particular, we standardize the fields U1 and U2. And we do that by subtracting the corresponding means and dividing by the standard deviations. And the reason we do this is easy to see if we consider having two different records. So suppose I have a record U and a record U tilde. And then I'd like to say, well, how close are U and U tilde? Well, let's just write that down. Well, then U minus U tilde, the 2 norm squared, that's going to be equal to U1 minus U tilde 1 squared plus U2 minus U tilde 2 squared. And so the first term in this is the difference in the number of bedrooms of house U and house U tilde. And the second is the difference in the price of house U and house U tilde. And both of those quantities are squared and added up. Of course, the trouble is that even a very small change in price is going to swamp a change in the number of bedrooms. And yet, a change in the number of bedrooms from 3 to 4 could be hugely significant, much more so than a change in the price from 200,000 to 250,000. So standardizing puts these two different fields on an equal footing within our embedded vector space. So then we're going to predict y is log v, the log of the price, from the standardized area and the standardized number of bedrooms. We'll have a linear predictor, which will be y hat is theta 1 plus theta 2 x1 plus theta 2 times x2. Plus theta 3 times x2, I'm sorry. And so in terms of the original data, we're going to, so how does this work? We start off with a bunch of data which we use in order to determine theta 1, theta 2, and theta 3. And then we get given a new house that we've never seen before, a new record, and that gives us a U1 and a U2, a number of bedrooms and a square footage. We take that number of bedrooms and number of square footage and we standardize them to get an x1 and an x2. We then apply our predictor, y hat is theta 1 plus theta 2 x1 plus theta 3 x2, to get a y hat, which is a prediction of the log of the price. And so our predicted price is constructed by inverting that embedding y is log v using v hat is the exponential of y. So v hat is going to be x of theta 1 plus theta 2 times u1 minus mu1 on sigma 1 plus theta 3 times u2 minus mu2 on sigma 2. And this is very interpretable. So for example, if here theta 2 is 0.7, what does that mean? Well, it means that every time u1 increases by 1 standard deviation, that means the price of the house is going to get multiplied by the exponential of 0.7, which is about 2. So every change in u1, which I think is area, every change in area by 1 standard deviation doubles the house price. Let's look at some more complicated embeddings where we take an individual field and embed it as a vector. So we can embed a field into a vector x is phi of u, and now x here lives in Rk, that's the dimension in which that particular field is embedded. And it's useful to have a k which is more than 1, even when the quantity that you're embedding, the raw data u, is just a real scalar. We've already seen that with the polynomial embedding, where phi of u is 1 u squared up to u to the d. And that's useful because it allows us to use a linear predictor to construct a predictor which is a non-linear function of u, even though the predictor is a linear function of x. And there are other things you can do. You can similarly use other nonlinear functions. You might embed it as 1 u minus u plus. It's worth drawing what these functions are. So let me try and do that. So this is going to be u. And then I'll plot the function u there. And I will also plot the function 0, which just sits right there. And then u subscript minus is the minimum of these two functions, which means that there is u subscript minus. And u subscript plus is the maximum of these two functions. And so that means that this here is u plus. So I've got two functions. We think about u plus as being the positive part of u, and u minus as being the negative part of u. Now what that means, if I'm going to construct a linear predictor with these two features, it means, well, let's write that down. So I'm going to have a linear predictor, which is a function of these two features. So I'm going to have y hat, which is going to be theta 1 plus theta 2 of u plus theta 3 of u minus. And so this is a constant. This is a linear function of u on the positive part of when u is greater than 0, and it's a constant when u is negative. And this is a linear function of u for when u is negative, and it's a constant when u is positive. What that means is that my function y hat is a function of u. I can plot it, and it will look something like this. It has a particular slope here, a particular slope here, and a particular intercept there. And those three quantities are determined by theta 1, theta 2, and theta 3. In particular, the intercept is theta 1. The slope of this part of the line is theta 2, and the slope of this part of the line is theta 3. And so I have a piecewise linear function. And it's also worth being aware that when one talks about piecewise linear functions, often one thinks about that meaning a function where the join, it is composed of linear segments, and the joins between the linear segments may be anywhere, and I may have any number of segments. Here, we're choosing predictors which are piecewise linear functions, but they're very specific piecewise linear functions. They only have two linear pieces, and the join has to be at the origin. The join has to be somewhere there. This particular quantity, the origin in this case, is called a knot for this piecewise linear function. That's K-N-O-T. And you might have more complicated piecewise linear functions which you could construct using a different embedding. So for example, if my embedding was 1 u plus, u minus, and u minus 1 plus, well then there'd be an additional knot out here at 1 when I'd be able to pick a different slope, and that slope would be determined by these additional parameters. Well, I've got 4 parameters, theta 1, theta 2, theta 3, and theta 4. It's worth noticing also that the slope of this line will not just be the coefficient in front of u minus 1 plus, but it will in fact be the sum of the coefficient of u minus 1 plus and the coefficient of u plus. Now then, a particular type of data field is called categorical, and what that means is that it only takes a finite number of possible values. In other words, the set script u is a finite set, and we've called the entries in that set alpha 1 up to alpha k. Those are called the category labels. Sometimes we'll use category labels 1 through k, and we'll refer to category I. Sometimes we'll be explicit about alpha 1 through alpha k and refer to category alpha I, depending on what works best at that particular notational point. Lots of things are categorical variables. The most common is the Boolean, true or false. There's only 2 possible values. We might be trying to identify fruit, in which case we might have apple, orange, and banana. We might have a field which is the day of the week, in which case there are 7 possible values, Monday through Sunday. We might have zip codes. That's 40,000 possible values, roughly. You could just say, well, embed that as a real number. But then we'd ask the question, well, is that faithful? And we might conclude, well, there's no particular reason why 2 zip codes that are numerically close should be physically close. Sometimes they are, and sometimes they are not. Countries, of course, they're not numerical at all, and so there are maybe about 180 or so different countries that we might list, and it's just a bunch of different categories. Languages, there are several thousand different languages, at least those which are spoken by a large number of people. Now there's a particular way of embedding categoricals which is very common and very useful, and that's called the one-hot embedding. So let's just refer to our categories now as 1 through k. So that script u has k consists of the numbers 1 through k. The value of the field is either going to be 1 or 2 all the way up to k. So the one-hot embedding says if you see u is equal to I, then embed that as e subscript I. Remember what e subscript I is? So in a vector space, E1 is just the vector 1, 0, 0. E2 is just the vector 0, 1, 0, 0. E3 is the vector 0, 0, 1, 0, and so on. People call it the EI, the ith canonical basis vector in a vector space. And so in a k-dimensional vector space, there are k different canonical basis vectors. And so we can embed the categories 1 through k as the k different basis vectors in Rk. So in particular, we might embed apple as 1, 0, 0, orange as 0, 1, 0, and banana as 0, 0, 1. We might embed true as 1, 0, and false as 0, 1. And this is a different embedding of the booleans into R2 this time, as opposed to the -1, 1 embedding we saw earlier. We might embed languages as a bunch of different canonical basis vectors, all the way up to 185 of them. And if we standardize these features, well, that allows us to handle unbalanced data, because when we standardize these features, they won't remain at 1, 0, 0, 0, 1, 0, 0, 0, 1. They will get shifted by the mean and scaled by the standard deviation. And in particular, the mean and the standard deviation of the data set will be affected by the proportions of the different categories that show up in the data set. And that's a nice way of handling unbalanced data sets. And we will see some of the problems that show up with unbalanced data sets later in the class. There's also another way of doing one-hot embedding, which is called reduced one-hot embedding. And here, the idea is that instead of mapping the categories 1 through k to k-dimensional space, we map them to k-1 dimensional space. The way we do this is we choose one of the categories, say the last one, category k, as the default value, the nominal value, and we embed that at the origin. All of the other categories, 1 through k-1, we embed as the first k-1 canonical basis vectors, E1 through ek-1, as before. If we do that for the booleans, then we would embed true as 1 and false as 0, because here k is 2, there's only 2 categories, and so Rk-1 is simply the real numbers, and so we're embedding booleans as 1 and 0. And this is a very common embedding of the booleans. There's another type of data, a specific type of categorical data, and that's categorical data that's ordered. Now, apple, pear, banana are very much not ordered quantities. There's no natural order to put the fruit in. But very often you do have orderings. So, for example, when you give something a rating on Amazon, and you're either going to give it 1, 2, 3, 4, or 5 stars. And yes, there's only 5 possible categories that you can put it in, but those definitely have an order. Such a scale where there's an order to the categories is, and it's used to indicate a preference, is called a Likert scale, Likert. And so, for example, the original Likert scale was strongly disagree, disagree, neutral, agree, or strongly agree. Likert was actually a person. It's not just a scale that measures how much you like something. Likert was a psychologist, an American psychologist who lived in Michigan. He lived for most of the 20th century. The Likert scale can be embedded into the real numbers with values -2, -1, 0, 1, or 2. And it's nice, it's a faithful embedding in the sense that it preserves the ordering of the different categories. It's also quite reasonable to treat the Likert scale as a categorical with one hot embedding into R5. That way is perhaps a little less faithful, but both ways are very common. You can do the same thing with other categoricals as well. For example, the number of bedrooms in a house. You could treat it as a real number, or you could treat it as an ordinal with values between 1 and 6. And both would be completely reasonable. So I want to talk right now about feature engineering. This is the next stage after embedding. So in embedding, we're starting with raw data, and we are putting that data into a vector space so that we can use mathematics to develop machine learning algorithms. The next stage is to think about feature engineering, and in feature engineering, the basic idea is that we start with some features and then we process or transform them to make new engineered features. And instead of just having a predictor which is dependent on the original embedding, we have a predictor which is dependent on these new features. And we can do this in lots of different ways, and we've seen some ways already. So one example of this is where we used a polynomial embedding of a real raw data. We embedded it as 1, u squared, u cubed, and so on. And you could either think about that as an embedding or as feature engineering, where we've chosen features in a particular way in the hope that it will improve our predictor. In that case, what it does is it allows our linear predictors to become polynomial predictors. Now, fundamentally, the question you have to ask yourself is, what feature engineering should you do? Does it improve the predictor? And there's an answer to this question that is worth repeating to yourself throughout this class. And that is that the way you tell whether one predictor is better than another is by validating the performance. So if you want to know whether these new features that you're producing using feature engineering are helpful, are better than the original features, then develop a predictor using the original features, develop a predictor using the new features. In both cases, validate the performance against unseen data. If the performance with the new features is better, well then your feature engineering is actually helpful. And if it wasn't, then you don't need to do that particular piece of feature engineering and look at something else. The point is that there is no answer to this question. There is no answer to how one should embed a particular type of data for a particular type of problem. The answer comes about through validation, through measuring the performance against a data set and determining whether the performance is better with that set of features. After the fact, sometimes you can come up with some post hoc explanation for why certain features were better. You can say things like, well, obviously for numbers of bedrooms one should use one hot embedding rather than an ordinal embedding into the reals. But there's no truth to such post hoc explanations. Those are just justifications for what happened, the outcome that happened to turn out that way. The only test, the only way of knowing whether one set of features is better than another is to validate. There are several different types of feature transforms. One is to modify particular features that you have. So you've got a feature xi, and you replace it with a transformed feature, xi new. So you might standardize, for example. Another thing you can do is you can say, well, I've got one feature, and I'm going to take that one feature and can create multiple features from it. That's the powers example. We take xi, we replace it with xi squared, xi cubed, and so on. Another thing you can do is you can take more than one feature and combine them together to create new features. So for example, you can take two features, say x1 and x2, and create a new feature which will be the product of x1 and x2. Here's a feature that's very commonly used. This is the gamma transform. You take x and you replace it with sine of x multiplied by the absolute value of x to the power of some constant gamma. And that produces curves that are shown in this plot right here. If gamma is a half, for example, it produces a curve that looks like that. That's a case where we might believe, for example, that a feature has diminishing importance as its magnitude grows. And so we might replace it, we might replace x by the absolute value of x to the power of a half. Again, that's a justification, but it doesn't necessarily mean that if a feature has diminishing importance that you should use the gamma transform. It's something reasonable to try, particularly if you're using a linear predictor, but the only way to know whether it's better or not is to validate. Another thing you can do is clip. This is also called saturation or Windsorizing. There's a nice little formula for it here. The new x is equal to x if x is between L and U, or it's equal to U when x is greater than U, or it's equal to L when x is less than L. And that saturates like this. And so values larger than, in this case, than 1 are just treated as if they're 1. Values less than -1 are just treated as if they're -1. We might believe that, for example, our data contains anomalies, very large data values that are really an artifact of the way the data was measured. And we know that the physical quantity that's being measured can never exceed values of 1 or -1, in which case Windsorizing would be a reasonable thing to do. Here's powers. We've seen these already. We know that this is u squared, and u cubed. And here's one we've seen already as well, u plus and u minus. These are splitting x into positive and negative parts. There's an additional one here which is worth looking at. This is the saturation function, sat of x. Sat of x is the minimum of 1, the maximum of x and -1. We can plot that. Let's try and do that. The maximum of x and -1, well, this is the -1 function, and this is the x function. So the maximum of x and -1 is that function right there. And then we take the minimum of that function and 1. And the 1 function is right here. And so the minimum of those two functions is, let me draw it right here. That's the sat function. It's the Windsorization. It's another way of expressing the Windsorization or the saturation function that we saw over here. Another thing one can do is create new features from multiple features. So we can model interactions among features. So, for example, you might create all products xi, xj, or you might create the maximum of xi and xj. You can also create all the monomials of degree 3 or less, x1, x2, x1 squared, x1, x2, and so on. And that would give us an arbitrary polynomial of degree 3. Products can be thought about as a nice way of modeling interactions, and so can maxima. So for example, suppose xi are Boolean, and we've embedded them to take values 0 or 1. And they might represent, say, patient symptoms. Then we create interaction features, which are the products of xi, xj. And of course, we only need to consider the terms for which I is less than j, because xi, xj is equal to xj, xi. So there are going to be, if we have d original features, we're going to add d times d minus 1 divided by 2 additional features. Then if we do linear regression, say when d is 3, we're going to get an expression which looks like theta 1 x1 plus theta 2 x2 plus theta 3 x3 plus theta 1 2 x1 x2 plus theta 1 3 x1 x3 plus theta 2 3 x2 x3. That would be the form of a linear predictor with those new features. Now these are very nicely interpretable, these coefficients, because theta 1 is the amount the prediction goes up when x1 is 1. Theta 2 is the amount the prediction goes up when x3 is 1. And theta 1, 3 is the amount the prediction goes up when both x1 and x3 are 1. In addition to theta 1 and theta 3, you get this additional boost in your prediction. And so this is saying that when two symptoms both occur, then we believe our predicted value of whatever it is we're predicting should have an additional amount added to it, theta 1, 3. Another way to say it is that if theta 1, 3 is large, then if you've got both symptoms simultaneously present, then we increase our estimate a lot. Another thing one can do in feature engineering is quantization. We specify bin boundaries, B1 through BK, and we partition the real numbers into buckets. The interval from B1 to B2, from B2 to B3, and so on. And then we replace x by the following. We embed it as E1 through EK plus 1, where the embedding returns E1 if x1 is less than or equal to B1. It returns E2 if x1 is in the next bin between B1 and B2, and so on. So x maps to EI if x is in bin I. This is a one-hot embedding of the ordinal that results from figuring out which bin x is in. And you might say, well, why would you ever do that? And the answer to that kind of question is always the same, is that this is the kind of thing you try and see whether it works. The only way to know whether or not it's better is to try it and validate. Sometimes you may believe that the case where x is in these different bins, those are really different situations, and so the predictor should treat them differently. And introducing these kinds of features is one way to develop a predictor that treats these different cases differently. That would depend on what type of predictor you're using, and so it's an intuitive motivation rather than a rigorous motivation. Ultimately, one validates to determine whether or not such a prediction, such a piece of feature engineering is a good idea or not. Now you can do these many times. You don't have to do embedding and then one round of feature engineering. You can compose them with each other. You start by embedding the original record U into a feature vector, which we'll call x0. And then you transform x0 using a feature engineering transform to get x1. That might be standardize. And then you repeat again. You might do a polynomial embedding, or you might do binning, or you might do Windsorization. And you repeat this m times, and you've got a composition of different feature maps, and that gives you the final embedding. And this is called the feature engineering pipeline. Now there's one more topic that I want to mention in this section, and that's automatic feature generation. So the features that we've seen so far are generally done by hand using experience. And that's hard to do. Essentially, it's done when one's trying these kinds of things. There are things that one knows are generally a good idea: standardization, logarithms, one-hot embeddings. And there are things that one has experience of in certain domains. Certain embeddings work well in certain domains. Products for symptoms, for example, is a very good thing to do. And then there is the rest of it, which is largely trial and error. One can try a bunch of different feature engineering tricks and hope that they improve your validation results. And because it's trial and error, it would be very nice to be able to develop feature mappings automatically, directly from the data. And this is certainly possible. We've already seen two examples. One is word to vec, where words were mapped to vectors. Another is VGG16, where images were mapped to vectors. And those were learned, and they were developed automatically from very large data sets. And those are very important methods. They have made a huge difference to our ability to do effective machine learning. And we will see later those methods in some detail. And we'll talk about some specific methods for constructing these things. PCA is an example of that. It stands for Principal Component Analysis. Neural networks is another example. So, to summarize, all features are mapped to vectors. That's embedding. That's the feature map. We subsequently process those vectors in our predictor. We may do extensive feature engineering to construct more and more complex ways of mapping features to vectors. Only validation can choose between different candidate feature maps. And we're going to see later how feature mappings can be derived from data as opposed to by hand.